that would happen, so I decided to have a little introduction to get us back up to speed, but that means I can pretty much skip that. I'm supposed to wait a minute or two before I get started. I've got to remember not to pick my nose because I'm being recorded.
Yep.
Is that okay? All right. Just a few words to get us going. Buildings are the main cause of global warming. I know I'm repeating the first few words here, but that's why it's so important for every one of you to take this seriously, because you're in the field where you can do something about it. Most people, no matter how interested they are in fighting global warming, they're just not in a situation where it will make much difference. Okay? Maybe they can vote for the right people, but you can actually make a difference by the way you do your job. And efficiency is what you're going to have the most control over. Photovoltaics is kind of a specialty, and it's something, it's like frosting on the cake. Right? You got to learn how to make the cake. And the low-hanging fruit is going to be kind of the framework of what we're going to do this afternoon. And I like the concept because it makes so much sense to do the easy and cheap things first. Ironically, the cheapest and easiest thing is the one that makes the most difference. That's really lucky, isn't it? It would be horrible if the most expensive and difficult. Orientation, orientation, orientation. And the frustrating thing is it's so easy and so little understood. So if you remember nothing else, just remembering that will make the biggest difference. So orientation and building color doesn't require a lot of words. White is the best color. If you can't do white, do the lightest color you can for the roof and the walls and the interior. Because electric lighting, you're putting out this light, anything but white is a sponge that soaks up the light and steals it from you before you can use it, right? Fortunately, that's well understood, so ceilings are usually white. But the back wall, even the front wall, it's absorbing most of the light that's falling on it. That's really not the best color. It may look nice, but okay. So that's it for color and window placement. So I'm going to be talking about four major parts of this solar strategy. Shading, and let me just remind you that if you really want to keep the sun out, because the sun coming in through windows is a major source of heat gain. That's where much of the air conditioning oil comes from. You got to shade it on the outside. The inside is better than nothing, but not a lot better. We're going to talk about passive solar first, how you can capture free winter heat. Then we'll do shading, and then we'll do daylighting. And one thing that we're not going to talk about, that's not in the solar, is a little bit of passive cooling. How you can, besides keeping the sun out, what else can you do to reduce the air conditioner load? Okay? So, let's see. Let's go to the first one. That's it. Passive solar is extremely simple, and every building that has a heating system should try to make use of passive solar. Passive solar can cost from nothing to a small amount. There's just no excuse for doing it if you have access to the sun. Now, not everybody will, If you're on the north side of a big mountain, especially around here, or in the middle of a forest, I'm not suggesting cut down trees, but there are many, many situations where you have access to the south. If you don't take advantage of it, it should be a criminal offense. I think you should be put in jail. Someday that may happen. Right now, not yet. Okay, so how do you do it? It turns out that any south window you have is a passive solar system. South windows collect more energy during a sunny winter day than they lose in a 24-hour period. They collect more energy during the winter than they lose in the winter. So every south window is a free source of heat gain. We don't want just a little bit, we want a lot. So the question is, how can you maximize that? How can you get as much free heat as possible? So that's where it gets a little complicated, to maximize it, not to have it. But the key element is south-facing glazing. The glass is a greenhouse device. The solar radiation can pass through, but the heat can't readily get out. So you have a one-way energy trap. Very simple. The ancient Romans already understood that. On a bright sunny day, especially in the fall and the spring when it's not real freezing out, you can collect so much sunlight that it'll overheat. You can go up to 90 degrees inside if you have a lot of south windows, which you want to have because you want to capture all the sun you can. Well, you don't want to be in 90 degrees, so what you do is open the window during the day and let that hot air out so you're more comfortable. And then at night you say, darn it, I shouldn't have done that. It would be great if you had stored that energy and you could use it at night. Right? Storing energy is an important part. Well, fortunately, that turns out to be really easy. Okay? If you have thermal mass would be something like concrete or brick or stone or water. If you heat that up, you can store the heat, and then when it cools down, those things will give the heat back off. So that's what we call thermal mass. So what you do is, I don't know if, can I point here? Okay. In this, we're now talking about the first of the three major passive systems. The first one is called direct gain, because the sun just comes in through the window and you've got heat. You want that sun to fall on mass, so that instead of heating the air, you want the air to heat a little bit, but you want to, most of that excess heat, you want to go into the floor slab, into the wall, depending on the situation, so that you're heating up the floor slab instead of putting all of that heat into the air. Then when the sun goes down, that warm slab will give off heat and keep you comfortable for part of the next night. Now, how long it keeps you comfortable depends on your window area and how much mass you have. So, in general, you want a lot of window area and lots of mass. Oh yes, let me reinforce what we said yesterday. Ask questions right away. Yes, please.
So on your second image there, that is essentially glass or glazing of some
You're getting
sort.
ahead, okay?
All right.
We're still focusing on the top. The top one, direct gain, is the simplest and the cheapest, and everybody can have it. Every time you have a south window, you have it. The more mass you have, the better. Now, it turns out, and I don't know about around here because of the hills, but most homes today are built slab on grade. It's cheaper than crawl spaces, which were the past. So, just because of what has been discovered to be the cheapest way to build in most cases, also turns out to be the best for passive solar, because it's the floor that mainly gets the sunlight. The wall only gets it if it's fairly close to the window, but if the wall is far back, it's the floor. So what you need to do is just expose the floor to the sun. Don't put a carpet on it. And it turns out, I think I have a picture of it, that we have ways of making concrete beautiful. We can acid stain it, we can polish it, and it's much healthier and cheaper than putting a carpet on. You know what carpet is? Carpet is plastic, and plastic is rigid. And to make plastic soft so it can be a fiber, they have to put in additives. And when you have a carpet with all these plastic fibers, those additives are given off, and it's called off-gassing. And it's called volatile organic compounds, which are poisonous. You don't want that. Carpet is the worst idea A wool carpet is okay. Yeah, go ahead.
So what about hardwood floors? How do they rate versus concrete?
Very good question. Wood, water is the best way to store energy. Water can store, the same volume of water can store 3 times as much as concrete. And if you can use water, use water. Now it turns out wood has water in it, right? Even dry wood. The less dry, the more water. So wood actually is a good heat storage. The trouble is, wood is a poor conductor. So if you have a wooden floor, the heat doesn't travel down to the lower layers of wood very much. And plus you only usually have, what, at most an inch of wood. So wood turns out, in theory, to be good, but in practice it's not good. So don't have a wooden floor where the sun is shining to give you passive solar.
Would tile be just as beneficial as concrete?
Okay. Because of concrete is a much better conductor than wood. So concrete or stone or brick or tile. And you have 2 problems. One is the conduction. So the tile and the concrete and the wood, the stone are all good. But you also need enough mass to store the heat for the whole day. So a tile alone isn't thick enough. But putting tiles on concrete is great. The first 2 inches do most of the work. The first 4 inches do all of the work. By the time the sun sets, the heat hasn't gone more than about 4 inches down. So having a foot of concrete doesn't do any good. You don't need it anyway, right? We're talking usually about 6-inch slabs. So the first 4 inches are going to be doing all of your thermal work. So putting tile on is great, no problem. Yeah, but it's not improving the situation, and it's not making it worse. Just changing the aesthetics, right? So if people don't want exposed concrete, then yes, give them tile or flagstones or something like that.
Now, what about in the case of a basement, like around here? You're just talking about slab-on grades. Probably most of the slab-on grades I'd venture to say around here were basement.
Yeah, that's why it's so important to design for the specific location. The thing to do is build on the south-facing slope of the land and have lots of windows into your basement. And let the basement slab be your solar storage. And heat will rise, right? Mm-hmm. So the upstairs, you'll get sunlight and heat, but you won't store much. But if you have a warm basement, it's going to keep the upstairs warm. Okay. You want the sun to fall on the mass. Okay. The mass that only gets warm air doesn't do much storage. The best thing is to have the sun actually fall on the mass. So concrete floor is the best option. And I've seen buildings like that. A lot of windows in the basement to store the heat there. Great questions, great questions.
How about, I own an old home, right? So how about retrofitting? Has there been much investment in that?
That's where water comes in. Okay. I don't know if I have a photo with me today, but you can buy tubes made out of fiberglass.
Like a radiant floor system, is that what you're talking about?
No. No, the radiant floor is not useful for passive solar.
Okay.
If it's wood radiant floor. Okay. I'm not saying radiant floor is bad. Okay, let's not misunderstand. But a radiant floor is not useful for passive solar. If you have an existing building, get some containers of water. Just the cheapest way would be to get milk bottles, let's say gallon milk bottles, fill them with water, and leave them exposed in the area you want to heat. Maybe put them inside the window so the sun shines through. But water stores a huge amount of heat. The water circulates, so it can be thicker than concrete. And it's the best storage. But you want to, how do you make it aesthetic? And that's where these fiberglass tubes that you can buy anywhere from 8 to 16 inches in diameter, and you have in effect these columns in your room that are filled with water, and as the room heats up, it heats up the water. And then when the sun sets, those water tubes are giving off heat, and they're beautiful. And they don't take up a lot of room, right? A 1 foot diameter water tube just takes up about 1 square foot of floor area.
Interesting. So have they explored like thermodynamics in the sense of putting a relatively large system of tubing in that maybe went around the top of a room,
Now,
right?
remember, in this system, we're talking about passive solar. You don't want a lot of complications. You don't want pumps or anything. That's active solar or hybrid. Right now we're talking about something that has no moving parts. You need to have the water sitting where it's exposed to the heat. Ideally directly to the sun, but at least to the air in the room.
I mean, with thermodynamics, the cold air would rush to the heated water, or the cold water would rush to the heated water, therefore creating a natural circulation. If you
I see what you're saying.
You see what I mean?
Yeah. Let's keep those questions for later.
Okay.
Be happy to talk with you. What
Understood.
you're talking about is a more sophisticated, complicated way of doing this. Okay.
Okay.
First, you want to learn the easy way. Right?
Grab the lowest hanging fruit, right?
Right. And if you're technically inclined and you're interested, you can improve on these. But what you're saying is true, right? But it's, for most people, you want to keep it simple. And direct gain is the simplest. If you have concrete slab, we're talking about no cost. And you want a lot of south glazing. Does that mean you add windows? No. There's a good logic to take some of the east and west windows and move them to the south. So we're talking about a system that costs nothing or a small amount and delivers a lot of heat for the life of the building. It's good. Every building that has a heating system and that has southern exposure should be utilizing this. Okay, any other general questions? Detailed questions or special conditions, let's keep for the break or afterwards, okay? But any question that deals with the concept or understanding the concept, ask it right away. All right, now, suppose you're rich and you have 5 Rembrandts in your living room, but you're, conscious about sustainability, so you want to do the right thing and you want to use passive solar. What do? Because light degrades colors of all kinds, fabrics, furniture colors, paintings, okay? The more light that shines on them, the faster they degrade. You do not want to take anything precious that is organic in nature, like paintings or some fine tapestry, something, and expose it to a lot of sun. The best thing is keep it in the dark, but of course then you can't see it. The next best thing is to have as little light on it as possible. So such a person would want passive solar heating, but limited amount of light, just enough light so you can see the paintings, so that you can enjoy the room, but no more light, but you still want more heat. For that comes the second passive solar strategy called tram wall. That's the middle image. Okay? Tram wall is named after a French engineer who invented this about 1950, and his name is Trombe, Trombe. That's French. They pronounce it Trom. Trombe is the way I would pronounce it. So he experimented with this in France, in the mountains, and it worked. And then wrote a paper, and it turns out to be a great idea. A wonderful way to get heat without light, which is not your first strategy, because you also want light, but if you want more heat than light, then that's your technique. In other words, you use them together. There's almost never a situation where you want only heat and no light. Can anybody think of such a situation? What kind of space would you want heat but no light?
Dark room?
Yeah, but how many dark rooms are there?
Anymore? None.
And
right?
chances
All
are the
digital.
dark room is going to be in the center of the building, where it doesn't need any windows, and the center of the building doesn't need heat, right? So mixing direct gain for light and heat and tram wall for just heat is probably the best approach to reducing the energy as much as possible in a desirable way. Now, how does tram wall work? You need glass facing south, that's the magic, and you need mass. and you put the mass just inside the glass so that the light gets absorbed. The mass of, it could be concrete blocks, for example, or a brick wall. This side facing the glass is painted black. So when the sun shines through the glass, the heat is trapped by the greenhouse effect. It hits the black surface, it's absorbed, and heats up the wall. The heat will travel into the wall, and heat travels very slowly, even in good conductors. Okay, so if you have a 8-inch thick wall, it takes about 8 hours to get all the way through, which means you don't really get any heat during the early day. You get the heat late in the afternoon and evening, but that's when you need it. That's when the direct gain is no longer working, right? So the time lag, that's what it's called, the time lag between when the wall absorbs energy and when it gives it off is desirable. So you get more heat at night. If you don't have Rembrandts, you use enough direct gain to heat you in the day and use the trom wall to get more heat for at night.
So what do you do in summer? You don't want, obviously, more
Yes,
heat.
yes. I'm going to have another presentation on shading, and it's appropriate to ask that here. It's very human to focus on one problem at a time. So there are lots of passive solar buildings that work great in the winter and then are terrible in the summer. And if you have air conditioning, all the energy you save in the winter you lose by air conditioning, right? So you don't want passive solar in the summer. And you have to shade the windows, and you have to block the sun from getting to your trom wall. And the best thing to do is, remember, shading should be the outside. On the trom wall, the best thing is to put a screen vertically on the glass. It's better than putting a screen between the glass and the wall, because then the heat is again inside. So instead of, let's say, an awning coming out over the window so you can still look, but blocks the sun, you have an awning that comes straight down. It's like an outdoor roller shade to block the glass so you're not heating the trom wall in the summer. Yeah. In all climates of the United States, maybe not in Alaska, but I think even there, you cannot just deal with one season. You have to design buildings so it captures the heat in the summer and not in the winter. No, the other way around. I did that to see if you were paying attention.
So have they done a study based on the wall thickness to find out the optimum wall thickness? Because you said about 4 inches is really what you need to capture that heat on.
Now this is
example
different.
number 1.
Okay, good point. The floor, 4 inches is about all you get that does work. On a rear wall, it's really about 2 inches because it doesn't get a lot of, if any, direct sunlight. But the trom wall, every square foot of trom wall gets sun all day long. See, on the floor, sun moves across, and so it doesn't spend, you don't get the sun puddle on the same spot all day long. And that's why you only get 4 inches. But in the trom wall, because the sun shines on every square foot all day long, more of it absorbs heat. Okay? And probably 12 inches is the maximum. Otherwise, too little heat gets in. 8 to 12 inches is usually what these walls have.
So my second question on that same is the glazing of the window. How important is that in the trom wall? I mean, I could see it would be advantageous to create as much of an insulation barrier between the window and the trom wall as possible. But I don't know.
Okay, let's talk about windows because that question also applies to direct gain. If you have single glazing, you get the maximum sunlight coming through, but you also have the maximum loss, right? You get double glazing, you have less loss, but you also get less sunlight. Every layer of glass adds to the insulation, but blocks some sunlight. You can buy R6 windows fairly readily today. They probably have 3 to 4 layers of glass. The amount of sunlight that comes through is greatly reduced. So you've got a problem. You really want the maximum sun penetration and the maximum R value. And there's no easy solution to that. So the the usual choice is double glazing without a low E coating. The low E coating really interferes with solar gain. So on your passive solar windows, use clear glass double glazing, no low E. If you want to, actually it's good you asked that question. What I recommend is night insulation. Okay? At night, it's very common, I do it at home, I close the drapes or pull the shade because I don't like that black hole effect. Well, that also reduces the heat being lost, but not a lot because the heat gets around those. So night insulation means you cover the windows on the inside with something that does a fairly good insulating job. The most popular product is a window quilt that rolls up and you pull it down at night and it runs in tracks so there are no air leaks. And it's terrific because then you have high solar gain during the day and you have very low loss at night. Okay? And then you can use that blanket also in the summer when nobody's home to keep the heat from coming in. So the ideal is clear double glazing and night insulation. Then you capture the most heat.
And you see it as beneficial to get, for instance, like low E glaze or low E on maybe the east and west and
Yes.
south facing.
A very important concept which the industry, the window industry, is fighting as hard as they can. Builders too, because they don't want to be bothered with this and it's too complicated. They want the same glazing on all facades. A terrible mistake. You're absolutely right. On the east and west, you want low solar gain, high R value. On the north, you want high R value. Okay? You basically need two kinds of glazing. Every building should have at least two different kinds of glazing. And it's a big battle to achieve that, but it's only by doing that will we ever get really low energy buildings. Okay? Nobody said it's going to be simple. So your questions are great and preventing me from hiding things that I should be telling you. All right? So, a mixture of direct gain and trom wall. Now, building a wall, a trom wall is not free because the windows, you can't say, I have the windows for view. You don't have the view. And we usually don't have a massive wall inside. Sometimes you could use it to hold up the building. That would be fine. But that usually, so a trom wall costs some, but it's not very expensive. Okay, double glazing, no low E is not that expensive. It's fixed, no operable windows, and a concrete block wall with the cells filled. It's really not that expensive either. So it's very doable. And the payback is probably somewhere between 2 and 5 years. So it really makes sense to do that. Now, there's a third, which probably is the most popular passive solar system, and that's called sun space, where you add another room to the building that you wouldn't have otherwise, that has a lot of glass, and you go into that when the sun is shining, and it's just delightful. I have such a room. I converted a carport into a sun space. And that room is just delightful in the winter. Everybody hangs out there. It's flooded with sun. It's bright and cheerful. It's warm. But it's an intermediate space. It's not a regular space of house. You don't air condition it and you don't heat it with a heating system. Because if you do, it's going to be a net loss. So this space is going to be wonderful, but you have to accept that on a cold winter day, when the sun sets, it's going to get cold. And what you do is you leave the room, you leave the sun space, close the door, and retreat into the house. Okay? On a real hot day, real hot sunny day when there's no wind, it's going to overheat because you have no air conditioning and you don't have enough ventilation, and so you don't use it on that either. You'll find that you can probably use it about 90% of the time when you want to use it. And it's a delight in the summer when it's not too hot, and in the winter when it's not too cold. Very expensive, because you're actually adding to the size of the building. This is the most expensive, but people have money, this is what they get, because it's so delightful. So you can't justify it on the money it saves. Can't justify it on being low cost or free. It's an amenity. It does contribute to the heating of the building, but not a lot. It's the least efficient of the three systems. So I don't recommend it to save the planet, to save money, but it's easy to convince owners because it's so delightful and they're willing to pay extra. You know, it's like the difference between buying a car that has a lot of extra features and a car that's just stripped down to the bare minimum. Most people are willing to pay a little extra, right? So this is an option, but it's the least important as far as saving energy. Now here's physics. You will hear from me and from everybody else in the world a mixture of opinions and facts. Okay? And often people will tell you what they think are facts, but it's really opinions. This is a big problem. So this is why you need to have a critical mind and you need solid information so you know when people are telling you opinions and not facts, especially when the opinions are wrong. Now facts can be wrong too, but then they're not really facts, they're errors, right? So what I've told you so far is true because passive solar has been around over 50 years, it's been tested, it works. Right? So we know from experience that it works. Here's physics. If scientists have measured the amount of solar radiation coming in through the glazing on a typical sunny day, different climates, different elevations, different parts of the world, and they plot that. And when you sum that all up, this is what you get. This is typical, this is for 42 degrees. You're here at what, 36 or something like that?
35.
Okay. The logic, 35, thank you. The logic is the same, the curves would be slightly different, but the conclusions are the same. All right, what are the conclusions? The bottom axis is the time of year, and the center is the winter. D is December, January, February, right? And the ends are summer. Now, what do we want from our windows? We want the windows to collect a lot of sun in the winter and very little sun in summer, right? Isn't that logical? So, which of the orientations? We've got curves for different windows, for south windows, for east and west windows, north windows, and skylights. We're talking about the purest kind of skylight is on a flat roof, a hole in the roof with some kind of rain shield, right? So all of these curves have their minimum in the winter and their maximum in the summer except one. Which one? Which one collects the most sun in the winter and the least in the summer? South. Okay. This is another, that's why south is so important. Because even if you do nothing, your south windows are going to collect a lot more sun in the winter than the summer. Now you can improve on that as we already talked, right? You can maximize that. But even if you do nothing, a south window is what you want. It does what you want. It collects sun in the winter, much more sun in the winter than the summer. All the other orientations do the opposite. East and west, the orange line, okay? What is it? They collect the least sun in the winter and the most in the summer. Is that what you want? No. What's the best solution to that? No east or west windows. Okay? Often that can be done, but not always. If you can't eliminate east and west windows, what's the next best thing? Make them as small as possible. Okay? What else? Good shading systems. Put a porch there. Big overhangs. Plant trees. There are all kinds of ways. Because they collect, they don't do anything much for you in the winter, they really hurt in the summer. North is not too bad in the summer, but it's worthless in the winter. So north is kind of neutral. It doesn't hurt too much, but it doesn't help. But the east and west are a big problem in the summer. South, if you could, you would do a building with only south windows. You think that exists? Absolutely. You can do that. Now, about 25 years ago, I was invited by Southern Homes and Gardens to write an article on skylights. They somehow found out that I know something. And so I wrote the article, not a long one, just a short one, and they refused to print it. You know why? Because I told them that the physics is that skylights are stupid. Skylights collect the most sun in the summer and the least in the winter. Why would you do that? Now, we do want to bring in light through the roof to light up interior spaces, but we don't want to do it with a skylight.
I was going to ask about solar tubes. I think they're called solar
Yeah.
tubes.
Solar tubes are tiny skylights. So what they still pick up more in the summer than the winter, but since they don't pick up a lot of sun, they don't do too much harm, and they do light up the interior, so I'm for solar tubes. And they come anywhere from, I think, maybe 8 inches in diameter to maybe 1.5 feet. So they're a good idea.
Wouldn't it depend on the angle of the skylight? Like if you orientated it so it would catch more of a lower sun during the winter period and less?
Yes, absolutely. Now, that's why I said we're talking about a flat roof with a hole in the roof. Okay, that is the purest form of skylight. Now, if the roof starts having a pitch, it's no longer pure skylight. And if the roof is vertical, then what is it? Then it's a window, right? So a skylight slowly changes into a window. A dormer. Everybody know what a dormer is? Very popular around here. A dormer is vertical glazing, right? It's on the roof. Dormers are great because they bring light to a place that would otherwise be dark, but then don't pick up more sun in the summer than the winter. The ideal thing is a dormer facing south, because a dormer facing south is a south window. It's exactly the same as south, but it's bringing light into the interior of the building. The general term for dormers, I have a picture, is clerestory. Clerestory is any glazing above the roof that is vertical. Okay, that's what you want to do. I'll show you some examples. So, did I just tell you opinion? No, this is physics. I didn't create these curves, pretend. This is reality, okay? And that you can rely on. That is absolutely true. It's not going to change 100 years from now. That remains the same. And the conclusion is, south is the ideal orientation. East and west is the worst. No, not the worst. Skylight is the worst. East and west is the next worst. North is kind of neutral.
Have you seen anything on where the tipping point is for solar south-facing skylights, for instance, like if it's a 12-12, right? So it's essentially 45-degree angle.
Put a dormer on. It's that simple. People love dormers. No, I'm not kidding. They will pay extra for a dormer. Plus, the dormer allows you to have, to make use of an attic,
Yeah,
right?
yeah.
So I would never put a skylight, even a 12-12. I would use a dormer.
Okay.
This is a picture of acid-stained concrete. I actually have it in my own house, and it's beautiful. I did it myself. It's not so easy, but it's the most sustainable. You basically take ordinary concrete, you buy this acid etching material, you spread it over. There's a chemical reaction. It's not a paint. The concrete actually changes color. Then you put a sealer on it. You're not adding that acid stain gets washed away. There's nothing left, no pollutants. Okay, not like carpets, which are off-gassing for 20 years and poisoning you. This is healthy, and you're not putting additional, carpet costs additional money, even if they're cheap, right? Here, the acid stain isn't that expensive. And so you're getting the cheapest and the best, and as far as I'm concerned, the most beautiful. It's worthwhile talking about carpets. Why are carpets so popular? Anybody know? Let's go back and go ahead.
Relatively comfortable, right? You can walk around without shoes on, soft on your feet.
That is true.
Got another
If
one.
you go back in history, let's say 100 years ago, what did people around here have on their floors? Well, probably dirt. Many of the houses they were on the ground, or they had wooden floors, right? Now, what did the rich people have? They had wooden floors with little carpets, maybe from Persia or something. The middle class always wants to be like the richer class, okay? but carpets were too expensive. They just couldn't afford them, so they just had wooden floors, and if they could afford it, they would have hardwood floors. Everybody wanted carpets because that's what the rich people had. So then when technology made carpets cheap, everybody got a carpet in their building. And the carpets got so cheap that they were almost cheaper than hardwood floors. What did the rich people do when everybody had a carpet? They got rid of their carpets and they had hardwood floors. Now what is the middle class doing? Getting rid of their carpets and going to hardwood floors. Right? So that is the reality, but it's not because of function, it's because of what a major force that drives us, status. Wanting to be like others, especially people who are richer than us. We really copy the poor. Why don't we just get rid of that kind of a motivation and go to what's healthiest for us and the planet? Okay? And if you have a concrete slab, do this. If you're raised, then just leave the wood exposed. Use a hardwood floor. I actually lived for, I have a second home in Colorado, which I was a general contractor for. And for over 15 years, we lived on the subflooring. I cleaned it off, and I gave it several coats of varnish. It was beautiful. It worked. Didn't even need a hardwood floor. Finally, last year, I got a hardwood floor. Because I only get it when I can afford it. I don't go to the bank and borrow money to get something I don't really need. Right? I pay, you know, when you get a mortgage, you end up paying twice of what, if you buy a $200,000 house with a mortgage, you end up paying $400,000 for it. But if you build the house as you have money, then you just pay $200,000. Actually, you pay less because you can do a lot of it yourself, right? Okay. What is the most important concept in creating a low-energy building?
Getting rid of east.
I know it's repetitive, but it's so important and it's so underutilized. Orientation. Okay. And this shows you a little bit, this is the same slide I showed you earlier. It's because of the way the sun moves around a building. The sun rises north of east in the summer. On June 21st, it rises furthest north, spends the whole morning in the eastern sky, shining on into east windows. Then it's kind of high in the sky, shining on the roof around noon hours. Then it spends the whole afternoon in the western sky, shining into west windows. And then it sets equally far west, north of west. Okay, that's the summer path. In the winter, the sun rises south of east and sets south of west, which means really only the south windows get the sun. That is where the logic of that graph, that's the explanation of the reality. If the building is not oriented right, you're never going to get a real low energy building. It's just a lot of opportunities are lost. Okay. Now, this shows you in a mathematical way the value of mass. Okay. They actually built two buildings side by side, identical, except one had a wooden floor and the other one had a concrete slab for a floor. And the slab wasn't covered with carpet because carpet is an insulator, right? So you've got to cover it with something that conducts it. And they measured what was going on inside. They turned the heating systems off in both so that the temperature side was purely a function of passive solar. This was a cold winter day, so the blue curve is the outdoor temperature. Notice that in the upper and lower graph, that curve is identical, right? Because it was same day for both buildings standing side by side. In other words, it was, if you look at the temperatures, a winter day was cold. Okay? It's less cold in the day when the sun is shining and colder at night when the sun is not shining. That's why you get the curve. Now, which of these, looking to see if it gives it away. No, it doesn't give it away. Which of these two curves is the one that has the mass, the slab floor? Okay. Well, you look at the red curve, which records the indoor temperature. And in the lower graph, the indoor temperature did cycle during the day, but not a lot. And the yellow bar is the comfort range. The ASHRAE official comfort range is from 68 to 78, okay? And people are basically comfortable in that range. You may, put on a sweater at 68 and you may take it off at 78, but that's a range that is fine for air conditioning and heating systems. And you notice that the indoor temperature, purely from the sun, was almost completely in that. And that's because of the mass. The mass soaked up excess heat during the day and then released at night. On top, with the wooden floor only and no mass in the building, the indoor temperature swing was wild. It got very hot in the day and very cold at night. Okay? So this is a good way of proving the importance of mass. I asked you if you could have a building with south windows only. Well, it's actually not so hard. This is a real building in Taos, New Mexico. It's a state office building, and every window in the whole building faces south. The windows on the south facade face south. The windows on the east facade face south. The windows on the west facade face south. And the windows on the roof face south. It's actually a very interesting looking building. Now those are called clerestories. When you get the glass going over the roof, the name changes from window to clerestory. When you have a window that's above the roof, either the whole roof or part of the roof, then it's called a clerestory. And here's another one. This one is in Colorado, in the mountains. It's a community college called the Colorado Mountain Community College, and it's a fairly big building, and this building only has south windows. On the east side, it's built into the mountains, so really couldn't have any windows there anyway. On the west side, it's exposed to the western sun, but no windows. All the windows to the south. To get light to the northern end of the building and the center of the building, what did they do? They have these clerestories up high, set further back, so you can get light to almost the whole building if you by having these clerestories. Okay. Now the windows on the south look kind of funny. Those are trom walls, and the architect didn't really work that out, right? How to shade them in summer, because this is a summer picture. So I don't know what they did. They hung up something. It looks very crude. It points out that that is part of the problem, is shading those trom walls in the summer and having, if you look on the right-hand side, you can see some awnings to shade the windows in the summer.
So they have that electrically charged glass now, where it can become opaque with some kind when you introduce electricity. Is that something you're seeing used more and more? Because if you put that on a trim wall, then you just flip the switch during the day, right, in the summer, and then even though it's opaque, is that something you've seen?
Yes, it exists. There are many dynamic glazings. Some are controlled by voltage, some are controlled by light. You may all know about the eyeglasses that darken. Some are controlled by heat. Okay? And they all will have a role, but they're not the ideal solution. Okay? On the trom wall, they actually may work quite well if they go from transparent to white. But some of them go from transparent to black, which would not be good, right? And in window glazing, you don't want to lose the view. A overhang, like an awning, allows you to have the view without blocking the sun. In other words, it's selective. It selects which light rays come in, which don't. Dynamic glazing doesn't do that. It blocks the view as much as it blocks the sun. So I see a small role for that stuff. Right now, it's still very expensive, and it's only been used in a few buildings. Okay. It does work. Some of them go from transparent to like sunglasses with a low transmission, but you can still look through. That's a better product for view glazing. But it still blocks the view and the sun the same percentage. Right? Much better to block 100% of the sun and maybe none of the view. This is the interior of the lobby. It's kind of an atrium, and it's this circulation hub, and it's lit up by these clerestories, and this is where they use thermosiphon because hot air rises. So in the winter, all the hot air is at the ceiling, and none in the down where the people are. So they actually use these ducts to collect the hot air and then bring it back down. In the summer, high spaces are great. Hot air rises and people inhabit the low space. Okay. This is a close-up of that building with the awnings in the summer. Can you see the skylight? Not very large. In the foreground, just beyond that orange, there's a skylight here, and then there's a skylight there, and then there's a skylight here. Okay. The original architects knew enough not to have big skylights, but they didn't know enough to have none. So they actually had to fix the problem because it was so bad. And they bought these triangular pyramid-like shading devices that are supposed to be on the north side in the winter, so they reflect light in, and on the south side of the skylight in the summer. But obviously it's not working. So it would have been better to leave those skylights out. I showed you this picture on Monday, and part of one thing I said is the south facade is so precious. It is, if you're religious, God gave us the beauty of the south facade to make use of. And it's just foolish not to make use of it. Every square inch can do work for us. So here in this building, we have direct gain. That's the glazing on the wall. We have trom wall underneath that. We have the clerestory for light and heat for the further north. And then instead of wasting the roof, they put photovoltaics on the roof. So every square inch practically of that south facade, including south part, facing part of the window, is being put to use, yes.
So, like, back to the community college, like, educational buildings, they usually have a central hallway going straight down through the center of the building. And then, so if you've got classrooms facing your south side with all the windows, how do you expose the other side of the hallway, which would be on the north side? How do you go about that?
I haven't been in that building in a long time, so I don't remember exactly. If I remember correctly, almost all the south glazing is offices, not classrooms.
Okay.
Classrooms definitely benefit from daylight, but people generate a huge amount of heat. And usually the problem becomes overheating rather than being too cold. When you come into a classroom in the winter, it'll be cold initially, but pretty soon it'll warm up just from the people. So I think in this building, I'm not quite sure how they get daylight into classrooms, if they do at all.
Okay.
One second. Increasingly, because of all the audiovisual, it's really questionable whether classrooms should be daylit at all. Like this room would not benefit from daylighting, right? How many times does it get used when there is not a projection? These screens are not being used. So.
Couldn't essentially what they do is the lower level you see in that be the classrooms on the south side, and then the upper level that you see where the higher lights are, the higher windows are, be the south side classrooms or the north side classrooms.
What you're really saying in a broader sense is that the way you design the building initially is critical, right?
Yeah.
And do you remember the building I showed from NRail, the office building? It basically had two slabs, both running east-west, because one couldn't handle all the functions. So that would be a way to design a school, that instead of being just one big mass, there would be two masses, that each would have a south wall. I just don't remember enough about this building to tell you in detail. But your questions are pointing out the right dilemma, and it's the initial design of the building, the form and the orientation that it has to be used to solve that, right? The architects play, of course, the major role in that, but they too often don't focus on the energy part, and that's why they need help. So that if in the future, if you're part of a team and the architect comes up with a scheme with the building running north-south, you say, whoa, let me take out my my graph here to show you that this is, this is not right.
Whip it out.
This is, I mentioned on Monday Amory Lovins, remember that name? You really should get to know that name. The Rocky Mountain Institute that he founded produces some of the best information. It's a think tank on energy. And he started this work about 30 years ago, maybe 40 years ago, and he wanted to prove that it works. At that time, everybody was convinced that what we need is nuclear power, we need more power, that all of these strategies like passive solar, they're just counterculture things, they don't really work. That doesn't make any sense. So he wanted to prove that it works. So he built his home and office in the Colorado mountains to prove that it works. And it works beautifully. So how did he do it? Two ways. Efficiency, very thick insulated walls, super insulated windows, and passive solar. So the center here is a sun space. Because why? Because it's fun. And in that sun space he has a garden. And this is the garden. This house is at 7,400 foot elevation in the Colorado Rockies, and he grows bananas, and he eats bananas from his indoor garden. In other words, he's developed a tropical climate, and he has no heating system other than a stove, and the stove is needed occasionally. It's needed when you have a whole slew of cloudy days. That's when it starts cooling down and you need auxiliary heat. But that's not that common. That's a small percentage. It's maybe 10% of the winter. 90% of the winter, the building is heated only by the sun.
Is his heat coming from the skylights up there?
Yes, the skylights play a big role, but this was one of the early passive buildings, and now this is my opinion, that sloped glass is more of a problem than it's worth. It increases your winter gain, but it also increases your summer gain. Sloped glazing is dangerous. You got to use special glazing. It's hard to shade. It leaks often. So my conviction is don't use sloped glazing. Just use south glazing. We know south glazing is pretty good for collecting the winter sun and not the summer sun. So if in the sun spaces that I design, only vertical glazing facing south. This is a place in Carborough, which is just next to Chapel Hill. My son rented a room here for a number of years when he was going to school at the University of North Carolina in Chapel Hill. And it's a co-housing. And the architect, I don't know if it's a he or she, did a really beautiful job. Thought of all kinds of things, and passive solar was one of them. But made a major blunder. Can anybody see what the major blunder is? These windows all face south. Yes?
Color.
Well, yeah, it's a blunder, but not a major one. Okay, these buildings would perform better with a white roof and white walls. So that's a mistake, but major blunder is sticking these buildings out. They actually shade each other. I took this picture in the summer, but in the winter, this window is shaded for half the day. Well, if you're only getting half the solar heating in the winter that you could, that's not good. So you basically need a fairly even south facade. You can have little jogs, maybe a foot or so. You can change the color, you can change the texture, but this was like shooting yourself in the foot. Okay? They spent extra money to make the passive solar work less. Which means you really have to know what you're doing. Okay, I'd like to also do shading, because it's so closely related. Your questions even pointed that out. and then we'll have a little break, and then we'll do daylighting and passive cooling. I think shading is this one? Yeah. I already talked about this. I was trained to be an architect during the time when modern architecture was dominant. And modern architecture got rid of shading devices and overhangs and got flat roofs and plain walls, and this was the philosophy. Well, which is more appropriate, short skirts or long skirts? Well, much of the year it's just pure fashion, right? Although it makes maybe sense to have longer skirts in the winter and shorter in the summer, but mostly fashion has nothing to do with function. And unfortunately, architecture philosophy was too much concerned with fashion and not enough with function. And one reason is they rejected the past. They said everything in the past was stupid. We now discovered, and that's a mistake. What we need to do is look at the past and learn from all the good things they did. They made a lot of mistakes in the past too, talking in terms of buildings. And then just take the good things, and only the good things from our modern knowledge, and combine them, and we get terrific buildings. So let me just show you some traditional buildings. What is the main characteristic of Asian architecture? Huge overhangs, right? Wouldn't look Asian if it didn't have these large overhangs. They're curved, but it's the large overhangs. Why did they have that? Because they need to shade the walls from sun and rain. They didn't do this because they thought it looked cool. They did it because it really works. It also looks cool.
So Frank Lloyd Wright played a pretty heavy hand in the modern movement. You think he had it maybe more right than some of his followers?
Yeah, I actually like Frank Lloyd Wright. He did a lot of experimenting, and when you do a lot of experimenting, you got to make a lot of mistakes. And people like to focus on the mistakes and not focus on the successes. Okay? If you experiment, you have to expect mistakes. We want to learn from his successes, not from his, well, you learn from his mistakes by not copying them. He went only halfway into the modern period. He's still, most of his buildings have overhangs and...
Yeah, which is what I mean, is he started out with Asian influence and large overhangs, but with straight lines.
Very good. You're absolutely right. So if you look at traditional architecture in America, overhangs and porches are a dominant part of it, right? So what we want to do to get a real high-performing building, that means low energy, is we want to harvest the winter sun and reject the summer sun. And in a big climate, that's going to be different. And also latitude changes sun angles. So there is no one answer for every building in the United States or the world. And what you have to do is look at your own local climate and see, how much of the year do you want to shade and how much of the year do you want to collect the sun? So here is a somewhat simplified analysis. It breaks the United States into 17 climate regions, and you can be more precise, but this gets you pretty close to the right answer. And let's see what would Charleston, South Carolina be a good choice for us if we were building here? No. Even though it's not that far away, it's a dramatically different climate. It's close to the ocean, it's at very low elevation. Probably Knoxville, right? Knoxville would be close. Not exactly the same, but similar latitude and similar climates. So in Knoxville, the black bar shows you how much of typical year you would want to shade. So you design the building so it's shaded for that amount of time. And then the blue hatched is the amount of time you want sun. So all the literature says, okay, what you do is you design your overhang so that the winter sun can get in and the summer sun can't. I used to say that too, until I did some experimentation, found out that doesn't work. Okay? And it doesn't work if you look, there's a line a, a center line, vertical center line, which breaks the year into half. It's the June 21st, the longest day of the year, the summer solstice. And what you find is that these bars are not symmetrical about that. But sun angles are, which means the thermal year and the solar year are out of phase. So if you think you can design an overhang that will keep the summer sun out and the winter sun in, turns out it's not possible. You need a dynamic system. Is it logical that you could have a static solution, like a fixed overhang, to deal with a dynamic problem? It's inherently illogical. You need a dynamic solution to deal with a dynamic problem. Okay? And what would be a dynamic overhang? An awning. Okay? You put the awning out in the summer and you pull it back in the winter. Now you get 100% shade in the summer and 100% sun in the winter. There are unfortunately a lot of myths. So here, let's look at this. The sun is shown when it's highest, June 21st, when it's lowest, December 21st, and the last day of the overheated period in this place. And so this overhang in the upper picture was designed to keep the sun out during the whole summer. But when you then look what happens in the winter, you see that part of that window never gets sun, even on December 21st. But winter is not just December, it's January, February, March, right? You want all those months, you want sun. Well, the window is shaded most of that time. So a fixed overhang does not work. The solar year, remember I talked about time lag? The solar year and the thermal year are out of phase. We get the least heating from the sun on December 21st. That's when the sun is lowest in the sky. We have the fewest hours of sunshine. It passes through the most atmosphere. That's when we get the least heating. When is it coldest in the winter? On December 21st? No, January, February is colder. Why is that? Because the Earth got warmed up in the summer and it takes time to cool down. The Earth gets the most heating from the sun on June 21st. Most number of hours, the sun is highest in the sky. Is that the hottest time of year? No. July, August are hotter. Why? The Earth is still cold from the winter. It is a time lag. And that time lag is part of the problem here. Okay. So the problem is complicated to understand, but the solution is real simple. Fixed overhangs don't work. Is a porch, a covered porch, a good idea on the south side of the building? No, because it's fixed, right? You're going to love it in the summer, but in the winter, you're not going to get any sunlight. So what you want on the south, if you have a deck, is an awning that you can retract. How about in east and west? Would that be a good place for a covered porch? Absolutely. Because you're not going to lose much in the winter, but you're going to gain a lot in the summer. What usually happens? The porch is facing the street, right? No matter which way the house is facing. Why is it facing the street? Isn't that true? The porch is almost
In
always
case you want to
facing.
sit out there and watch the traffic go by.
Yeah. How often is that the case? That used to be the case. Is that the case today in a modern suburb?
Now, hopefully you're not anywhere near a street, even in your own neighborhood.
Yeah, but even in a quiet neighborhood, do you see people sitting out on their porch?
Well, there's good television to be watched.
That's right. You could watch a nature program. You'd see the nature. You don't have to go outside. Why is the porch facing the street? The status symbol. Right? Porch makes house, it's decoration. It's not functional. You don't even go in the front door. It's not like, okay, you know, we want to protect the front door so you can collapse the umbrella. This was the first almost all glass office building in the world. This is the UN building. And it became the prototype. People say, it's different. It's exciting. We're going to do that from now on. So you get all these glass skyscrapers. There's no shading on this building. And that's a tragedy because it was originally designed to have shading devices. And I just keep thinking if they had stuck with that original design, all office buildings might have shading systems today. But that's what happens. That's psychology. This became the model. It was a bad model. Everybody copied the bad model.
What was
Not
the
against the UN.
What was the original shading system like? Do you know?
This was the. It's a funny story. This was a competition. The land was donated to the United Nations by Rockefeller, the rich oil man, one of the Rockefellers. I don't know if it was the original. And part of the reason was we wanted it in the United States, right? Which is nice, I think. So the land was there, and then the UN decided to have a competition. They wanted something special, right? And it was entered by a lot of architects, including Le Corbusier. And he came up with this solution. But if you know about Le Corbusier, he always had what he called sunbreakers. He was probably the most prominent modern architect to use shading. And he didn't get the competition. Competition instead went to an architect called Harrison. Harrison was a terrible architect. Why should they give the competition? It just turned out that Harrison was a relative of Rockefeller. Just coincidence. Okay? So Harrison didn't know what to do. He was smart enough to copy Le Corbusier. So that he actually, his solution was almost identical to Le Corbusier's proposal. But he wasn't smart enough to also use Le Corbusier's shading devices. He stripped that off, and we ended up with this. This originally had big concrete shading walls and overhangs. If you know anything about Le Corbusier's buildings, you could visualize what it was like. Actually, it looked a lot like this. Okay, this was very popular in modern architecture about 40 years ago. Exposed concrete, popular with those modern architects who believed in shading. And this was really Le Corbusier's kind of solution. Now, is the solar exposure of the east and west walls the same as the north and south? No, that graph showed they're clearly different. So should you have the same shading solution on all facades? Any building, if you go out, that has shading usually has the same solution on all. That shows a lack of sophistication. There is no one shading system that works on all facades. And but that doesn't mean that the building has to have no kind of unity, that you'd say, this is strange, you know, it looks like one building on one side and it looks like a totally different. So here's a building that no matter which way you approached it, you knew that you were approaching this particular building. Yet, no two facades are the same. In this case, the left facade faces south and the right facade faces east. And is there a difference between the two? Yeah. The one on the left has a light shelf. The one on the right has the light shelf rotated. Why? Because on the east side it's harder to shade, and so they had to do something. So it's similar but different. And then this is the other corner of the building. One of these facades is facing north and the other one is facing west. Can you tell which? Yeah, the north facade has very little shading because it's easy to shade the north. North does need shading, but not a lot. And then there's the west facade, which in this case is different from the east, but still it is very heavily shaded because the west and east facades get too much summer sun. And it has these vertical louvers that face northwest. So for almost the whole afternoon, the sun is blocked, so is the view. Right? There is no ideal solution for the east and west. That's ideal solution is don't have east and west windows. Now, suppose you said, all right, you know, I got a beautiful view there. I'm going to have east and west windows. I'm going to shade them with an overhang. Okay. How long does an overhang have to be to fully shade east and west windows? Anybody? 33 feet? If you, it's not on here, but the caption says this shades until 4 p.m. What about 5 p.m.? A overhang on the east and west has to be infinitely long to fully shade the sun. Well, it's a little expensive to build an infinitely long. 33 feet is pretty good, but still not fully shading. It's really impossible. So what do? There are cases where you have to have east and west windows. It's just, it's the situation, it's the location, the size of the lot, the function of the building. Sometimes you can't help it. And you do want to give people windows. This is one of the most sophisticated buildings in the world. It was built over 30 years ago, and it's still hard to beat. This was built in California. It's in Sacramento. It's a government building. It was built as a prototype. They wanted to, like Amory Lovins, they wanted to prove that you can build a low-energy building. Because at that time, it was not obvious that it could be done. But the principle is, if something has been done, it's possible. You can't argue that it's impossible if it has been done. So they wanted to prove that it can be done. And the side of the building in sun is the west side. So what they decided to do, they had to have windows. They have these external roller shades that automatically come down in the afternoon, and they come down as the sun sets. So at 12 noon, all morning and 12 noon, they're completely up, and there's no shading at all. People have beautiful view towards the west. Okay. Then the sun comes across at 1 o'clock. It's starting to hit the west facade, but it's high, so this roller shade comes down just a little bit. And then 2 o'clock it comes down some more, and 3 o'clock. Now what about on a cloudy day? All automated. On a cloudy day it doesn't come down. How about if it gets very windy and these fabric roller shades could get torn? There's a little weather station. If it gets very windy, they retract, and they've been working beautifully for 30 years. The shade is protected from rain, ice, and snow, and if it was designed right, it works great. It's guided by cables, so it doesn't flutter. Wonderful solution. Do you lose the view in the afternoon? Yes. But if you don't lose the view, then the sun will shine in.
So I have no idea if it's nearly that complicated, but I think we have a similar system in our rec center. That we have curtains that come down, but they are on the inside, so
Yeah,
that's probably
that-
not as helpful.
That is a very popular product. It is heavily advertised. They claim that it works fantastic. It works a little bit. Okay. It's better than nothing, absolutely, but not nearly as good as outside. Now, outside is going to be a lot more expensive because it has to be made weatherproof and more durable and so on, but eventually there's no way around it. That inside is just not going to be good enough. Unless you have something like that night insulation where a quilt comes down so that you have, good insulation between the window. But if you usually those shades are translucent, they're fabric, so you can still kind of look out. They probably block 10 or 20% of the sun. 10 or 20% of the sun's heat. They block a lot of the glare, but they don't block much of the heat. But again, they're better than nothing. Right? But what that company, it's called Mecco Shade, is the big one. If you read their literature, you think they've invented the perfect device. Okay? What they're giving you is slanted opinion, right? You don't want that. What you want is facts. And you're not going to get the facts from them. Actually, I have a picture of it. Okay. This is very, very common. And it's also a retrofit. So many of the buildings, especially airline terminals, are disasters, all glass, and the air conditioning can't keep up. It gets too hot. It's glary. So they either had these things designed initially or they added afterwards. And better than nothing, but it's not the best way to do it. You're never going to get an low energy building this way. You're just going to get a less bad building. So how do you shade buildings? Okay, so I'm going to show you some varieties, and this is a shading system in Denver. Most overhangs cantilever out, and that becomes a structural problem, easily solved, but takes muscle to have a cantilever, especially if it's piled with 4 feet of snow. So they decided there's a much simpler solution. Let's just have these posts outside, and tied to the building, and also to keep the shading system from being a sail catching the wind and to some extent the snow, they used louvers instead. I think this was a very smart thing to do. And it's attractive. This is shading on the north side. And again, you can learn so much from traditional architecture. Before air conditioning was available, what about the Biltmore? How did the owner of the Biltmore stay cool? Did he have a big air conditioning system? The original owner? It didn't exist, right? So I actually don't know exactly what they did, but they used the architecture to get all the comfort they can. One thing he did was to build up here rather than down in the lowland. And so here, this is a Italian palace in, I think in Venice, and you can see what they did in those days. They have outdoor roller shades, and they had those, maybe not this particular kind, but the concept has been around for hundreds of years. Then they have an arcade on the bottom so that the lower windows and doors and the people walking around could walk in the shade. And when the sun is low, it would get under that arcade. What they do? They even had roller shades for that. One of my convictions is that if I can prove to people that these shading was a standard part of traditional architecture, it may be easier to convince them that, this is not alien, this is traditional. It disappeared, shading disappeared when we had air conditioning and cheap energy. Now we find out that the cheap energy is not so cheap and it's hurting the planet. So what do? I'm not against air conditioning, but instead of it being this big, let's make it this big. Instead of using this much energy, let's have it use this much energy. That way you get perfect comfort with little energy, little destruction. And how do you do that? Well, in the summer you need to shade the windows. Now, where's shading used the most now in our society? As an advertisement. All the fast food places practically, the little better ones, they all have awnings. This is Barnes & Noble. Those awnings are not there to save energy. They're there because somebody decided they're beautiful. They really were they help shade the windows, but they were put there because they're beautiful. Well, if they're beautiful, why not put them and save energy, right? Too often, we are led to believe, okay, it'll save energy, but will end up being ugly. Well, that's not the case with an awning or a shading system. Ironically, the country in the world that has the most sophisticated shading is Germany. And Germany is much further north than we are, much cooler. They need shading much less than we do, and yet they use it much more. Now, why is that? Well, one reason is that energy is more expensive there. But the main reason is that Germany had decided about 20 years ago that they would become a very sustainable society. This was a conscious effort, and they were willing to pay for it. Okay? And they've done all kinds of things. Just several weeks ago, Germany produced half of its electricity with renewable energy. We produce less than 10%. So again, if it's been done, it's possible, right? And they're not stopping there. They've decided to get rid of their nuclear energy and slowly have as much of the electricity produced by renewables, and they're really pretty far there. Controlling the sun is vital. You don't let the sun shine in, then use electricity to pump it back out. So they've worked on all kinds of shading systems. The great inventions, I think I told you that. What are the greatest invention of humankind? Fire, the wheel, writing. What was the next one? Venetian blind. Okay, and then light shelves. We'll get to light shelves. Now, Venetian blinds really are brilliant. And why are they called Venetian? Well, I've never been able to find out. I've even asked Italians. Were they invented in Venice? Nobody seems to know. But they're brilliant. What's even better than an indoor Venetian blind?
Outdoor.
Outdoor Venetian blind. And so in Europe, especially Germany and Austria, these are very common. They're very well made, made out of metal, and they do all the things that the indoor Venetian blind do. They can move up and down, they can rotate, they can close, they can open, and on the outside they work about 4 times better than the inside. They're now available in the United States. I've never yet seen one used, but I think eventually you're going to but this is perfect for office buildings where light quality is important. Still need daylight, but you also don't want to waste energy. With a Venetian blind, and this picture I like because it shows different combinations, right? All the different ways you can adjust it. Why? Why is it so adjustable? Because the environment is very dynamic, and you need a very dynamic solution to deal with a very dynamic environment. I think I talked about biophilia. Did I talk about biophilia? No?
Oh, yeah. Yeah. Human nature for living things.
I have a great excuse. I'm old, so I don't have to remember. Okay? I love biophilia, the concept. But I also one reason I love it is because I experience it. I love living things. I love people. I love pets. I love plants. My wife has our house looks like a greenhouse in the winter because she has so many plants and brings them in. It's wonderful. I love to go to parks. The campus here is pretty green. Why is it so green? Because people like it that way, right? The whole thing could be covered with concrete painted green. So this is did I show you this picture? No. Okay, good. What kind of building do you think this is?
Apartment complex.
You really can't tell. But it's surprising. This is a school, a K through 12 school. Actually, it's a K through, 8 school. Wouldn't it be a nice place to have gone to school? Now, where do you think it is? It's in Bangkok. Could we do that here? Absolutely. Wouldn't look like that in the winter, but it could look exactly like that in the summer. Would that be nice? Does that shade the building as well as satisfy human needs? Absolutely. That's, I think, the way architecture should look in the future. Why do people go to the suburbs? Why are suburbs so popular in the United States?
Easier to find green space.
A lot of reasons. Escape, the ghettos, escape crime, escape dirt, but also to get to good schools. All of these are reasons. But I think one of the big ones is because it's more beautiful out in the suburbs. You got all this greenery. Now, what would happen if cities didn't have a lot of crime, had excellent schools, and looked like this? Would suburbs be equally desirable? There's one big problem with suburbs, commuting. It's terrible. You're wasting a good part of your life. Now, right now, the way cities are, it may be worth it. But suppose the city were like this, would it be worth driving an hour every day to get to a place that maybe look no better? This is an office building in Eugene, Oregon. And these are photographs at 4 different times of year of a detail of that. And that's one of the beauties, that buildings covered with plants change. And how many of you likes the fact that the climate has seasons? You can go to parts of the United States where there are no seasons. If you go to Los Angeles, there are practically no seasons. Almost every day of the year is exactly the same. Well, a lot of people like that, but it gets kind of boring. I've been there. It gets boring. I really like seasons. Okay? And here's another benefit, that if a building is covered with plants, it looks different at different times of the year. That's a positive thing. That's not a negative thing. Do people look different at different times of the year? Maybe not inside the room, but they look different outside, right? And what's one of the nicest thing in the spring is to see young people with less clothing on. After being totally covered in the winter, it's really special to see more skin in the spring. Now this you've seen, right? No, I'll skip that. We shading windows is most important, but really we want to shade walls, we want to shade roofs, and we want to shade areas around the building. And this is the only one of the kind that I've seen in the United States where this is a gas station in Florida, and what they're shading is the parking area and the area where you fill up. Why? Because it's so hot there in the summer that it's really desirable to shade not only the buildings, but the outside as well. This is a shopping center in Las Vegas, and they're lucky, the air is very dry, so if you're in the shade in Las Vegas in summer, it's not bad. But if you're in the sun, it's horrible. Just think of the hottest day here, it's like that. And it's actually, you start sweating because it's so hot, so you also have some of the sweating problems. So all they had to do was to create shade for the shoppers, and it had a wonderful climate. I was asked to be on a committee for the CDC, that's the Center for Disease Control in Atlanta. That is a government organization to protect us from illness and disease. Right? And the reason I was invited is that there is a epidemic of skin cancer in the United States. And it turns out that happened sooner in Australia. Australia actually gets more sun than we do. And Australians have a huge problem with skin cancer. And the reason is that nowadays, people stay indoors most of the time. And when they go out, they have fair skin, they get some skin cancer. In the past, the farmers and so on, they were out all the time. They developed a nice deep tan, and so they were protected. So ironically, by being less in the sun, it became more dangerous. And so in Australia, they passed all kinds of laws to, especially with kids, to protect them when they go outside to play. And shading the play areas became a very important feature. And we have to introduce that now in the United States. Okay? And that's what this illustrates.
Thanks, Australia.
How many people think white roofs are ugly? Okay, can we have a little break?
Yep.
Yeah. Actually, I talked longer than I planned before the break. How long a break? 5 minutes?
Yeah.
5 minutes.
I thought I saw
You talked to him to come in?
These little microphones are on.
Yeah.
Dude, look what I can do.
I'm trying to keep it to a minimum, but I can't help it.